In this video, we will explore the use of flag bits. Flag bits are commonly used by system calls when a single argument is used to transmit data about multiple options. That variable is treated as an array of bits, where each bit represents an option or flag that can be turned on and off. We will explore how this concept is used to implement file permissions. Before we start to look at the implementation, let's briefly review how file permissions work in Linux. Each file has an owner and a group. When I run ls-l on a directory, here is what I see. Let's look at how file permissions work in Linux. Here is the contents of a directory. The first column in the output is the permission string. This represents who can read, write, or execute the file. The third column is the owner of the file, and the fourth column is the group. The owner and group fields are relevant to permissions because Linux allows us to set separate permissions for the owner of the file, the group, and every other user in the system. Let's look more closely at the permissions for syscall-cost. The leftmost dash in the permission string identifies the file type. The dash means that it is a regular file. Results, which is a directory, has a D in this position, and a link would have an L. The owner of the file has read, write, and execute permissions on the file. The members of the group instrs has read, execute permissions on the file, but cannot write the file. Everyone else also has read and execute permissions. How does this relate to the bit manipulation operators and bit flags? If you ignore the first dash that represents the file type, each file permission is essentially an on-off switch, so we can represent each one with a flag bit. We need 9 bits to represent each permission setting, so we need a variable with enough space for 9 bits. This rules out storing it in a byte. The system calls that operate on file permissions use a mode_t type for the permission string. On my system, this is defined as an unsigned int, a 32-bit value. The permissions will be stored in the 9 low-order bits or rightmost bits. The first step is to see how to turn the permission string into a sequence of bits. Each character in the permission string becomes a bit in our variable representing the permissions. Bits 8, 7, and 6 represent the read, write, and execute permissions for the user. Bits 5, 4, and 3 represent the permissions for the group. And bits 2, 1, and 0 represent the permissions for everyone else. What if we wanted to represent a file with read-only permissions? That file only has the read permissions set. So we'd represent it with the binary value 100100100. As we know from the past few videos, we could construct that value with bitwise operators. Fortunately, the system calls that take a permissions variable as an argument use several constants to make it easier for us to construct these values. One of the system calls that operates on file permissions is the chmod system call. Looking at the man page, we can see that the arguments to chmod are the path to the file we want to set permissions for, and the mode or permissions to set. Looking farther down the man page, we see a set of defined constants which will make it easier for us to set a value for the mode. Note that these constants are defined in octal or base 8. Base 8 is convenient for representing permissions because one digit in base 8 is 3 binary digits. An octal or base 8 constant in C is written with a preceding 0. We can define constants for each possible permission. Here, for example, are 3 constants for setting the read permission. Now we can go back to our problem. We can create the permission value using the bitwise operators we learned about in previous videos. In this case, to set bits, we use bitwise OR with the appropriate constants. Similarly, we can check if the bits are set using bitwise AND. In this case, we combine the two flags for the group and other users using bitwise OR. Then we use bitwise AND to check if either bit is set. Flag bits are a compact, efficient method for representing data with multiple Boolean components. The use of individual bits, rather than whole characters or integers, saves space, while the use of bitwise operators is clean and fast.